Ben Nevis stands at 1,345 meters, 4,413 feet, Scotland's highest peak. Climbers reach the summit every day, thinking they have conquered the tallest point in Britain. They are standing on a ghost. 400 million years ago, the rock beneath their boots towered 3 times higher, maybe 4 times. The mountain they see is what is left after geology's greatest disappearing act, a peak that once rivaled the Himalayas, carved down to a fraction of its former self by wind, rain, and 400 million years of relentless erosion. This is the story of mountains that made Everest look ordinary, and the slow, patient forces that made them vanish. The proof starts with a rock. In 1997, geologist Simon Kelly held a sample of gneiss in his hands. Banded stone. Dark and light layers compressed over unimaginable time. He was working with a team from the Scottish University's Environmental Research Centre, using uranium-lead dating on zircon crystals trapped within the rock. The lab results came back with a number that changed everything. 3 billion years. Not 3 million. 3,000 million years. Kelly stared at the data. He ran the analysis again. Same result. The rock in front of him had formed when Earth was barely 1.5 billion years old. The planet's crust was still solidifying from the primordial heat of formation. The moon hung closer to Earth, and days lasted only 18 hours. The scientific community was skeptical at first. 3 billion years was ancient, even by geological standards. But subsequent studies confirmed it. The Lewisian gneiss, as it is now called, is the oldest rock in Western Europe. It formed when Earth had no oxygen in its atmosphere, no complex life in its oceans, no continents as we know them today. This stone is older than the supercontinent Pangaea, older than the dinosaurs, older than Scotland itself. And it is everywhere in the Scottish Highlands. Walk along the coast of the Outer Hebrides, and you are walking on Earth's deep memory. The same rocks that witnessed the birth of multicellular life. The same stone that predates almost every mountain range on the planet. But here is what makes the Lewisian gneiss extraordinary. It survived what came next. 430 million years ago, the world looked nothing like today. Scotland didn't exist as a place. It was part of a landmass called Laurentia, a fragment of crust drifting across an ancient ocean named Iapetus. To the east, another continent approached, Baltica. Modern Scandinavia, Finland, and parts of Russia moved westward at roughly the speed your fingernails grow, 2 to 3 centimeters per year. Slow, inevitable. Between them, the Iapetus Ocean began to close. Oceanic crust, the dense, heavy floor of the sea, dove beneath Laurentia in a process geologists call subduction. Picture a conveyor belt of rock descending into Earth's mantle, melting under pressure and heat, and triggering volcanoes on the surface. For 50 million years, the ocean shrank. Then, around 400 million years ago, the continents collided. The impact did not happen in a single moment. It was a grinding, crushing process that lasted tens of millions of years. The edge of Baltica slammed into Laurentia with the force of tectonic inevitability. Rock folded. Sediments that had lain flat on ocean floors for hundreds of millions of years crumpled upward, layer upon layer, like a rug pushed across a floor. And mountains began to rise. The Caledonian Orogeny. That is the name geologists gave to this mountain-building event. Orogeny comes from the Greek words for mountain and birth, and this birth was spectacular. The collision created a mountain range that stretched from what is now Norway, across Scotland, through Ireland, and all the way to the Appalachian Mountains of North America. Yes, the Appalachians and the Scottish Highlands are the same mountain range. They were connected until 200 million years ago, when the supercontinent Pangaea split apart and the Atlantic Ocean opened between them. If you could rewind Earth's history and close the Atlantic, Scotland and America would fit together like puzzle pieces, their mountains aligning perfectly. But here's the question no one can answer with certainty. How tall were they? Geologists study mountain ranges like forensic investigators at a crime scene, piecing together clues from what remains. The evidence comes from the rocks themselves. Metamorphic grade, the degree to which heat and pressure altered the stone, tells you how deep those rocks once were. The deeper they were buried, the more intense the transformation. In the Scottish Highlands, geologists found rocks that had been buried 20 to 30 kilometers beneath the surface. That's 12 to 19 miles down. To bury rock that deep, you need weight above it. Mountains. Pressure calculations suggest the peaks above may have reached 6 to 8 kilometers in height. That's 19,000 to 26,000 feet. For comparison, Mount Everest stands at 8,849 meters, 29,032 feet. The Caledonian Mountains may have come close. Some researchers argue they matched the Himalayas. Others suggest they exceeded them. The truth is, we'll never know for certain because the evidence has been eroded away. But what we do know is this. 400 million years ago, if you stood on the coastline of ancient Laurentia and looked east, you would have seen peaks taller than anything in Europe today, stretching as far as the horizon. How do geologists figure this out? How do you measure a mountain that no longer exists? The answer lies in a technique called thermochronology. It is based on a simple principle. The deeper you go into Earth's crust, the hotter it gets. Roughly 25 to 30 degrees Celsius per kilometer of depth. Rocks at the surface are cool. Rocks buried 30 kilometers down are hot enough to reset certain radioactive clocks within their minerals. Apatite, a common mineral in granite, contains trace amounts of uranium. Uranium decays into helium over millions of years, and helium atoms leave microscopic tracks as they escape the crystal structure. These tracks accumulate over time, like scratches on a window. But if the rock gets heated above a certain temperature, about 60 to 120 degrees Celsius, the tracks anneal. They disappear. The clock resets. So when geologists find apatite crystals in Scottish rocks and measure the helium track ages, they are seeing when those rocks last cooled below that critical temperature, when they were brought close enough to the surface to stop erasing the tracks. And from that, they can calculate how much rock was above them, how deep they were buried, how tall the mountains must have been to create that burial depth. The data from the Scottish Highlands shows rocks that were buried 20 to 30 kilometers deep, heated to temperatures exceeding 500 degrees Celsius, and then slowly brought to the surface as the mountains eroded away. The cooling ages range from 400 million years ago, near the surface, to 350 million years deeper down. That progression tells the story of mountains collapsing in slow motion, shedding their height layer by layer over tens of millions of years. And then, the erosion began. Erosion is easy to underestimate. Rain falls, streams form, rivers carve. It seems slow, incremental, harmless. But given enough time, erosion is the most powerful force in geology. It tears down everything. The moment the Caledonian Mountains stopped rising, the moment the tectonic forces that built them relaxed, they began to die. Water was the first weapon. Rain fell on the peaks, seeped into cracks, froze overnight, expanded, and split the rock apart. This process, freeze-thaw weathering, is devastatingly effective. Water expands by 9% when it freezes. That does not sound like much until you realize it exerts 1,400 pounds of pressure per square inch. That is enough to crack solid granite. Every night above the freezing line, ice broke the mountains from within. Every morning, the sun melted the ice, allowing water to seep deeper into new cracks. And every night, the cycle repeated. Millions of nights, millions of freeze-thaw cycles. The peaks fractured like glass under a hammer. Streams carried the debris downhill. Rivers cut into the valleys, deepening them, widening them, transporting billions of tons of sediment toward the sea. The River Tay alone, Scotland's longest river, carries roughly 250,000 tons of sediment to the North Sea every year. Multiply that by 400 million years, and you're looking at trillions of tons of mountain washed away. Wind scoured the high slopes. Chemical weathering, the slow dissolution of minerals by acidic rainwater, weakened the stone from within. Granite contains feldspar, and when water reacts with feldspar, it transforms into clay. Solid rock becomes mud. Landslides stripped away entire mountainsides in seconds, and over millions of years, the peaks grew lower. By 300 million years ago, the Caledonian Mountains were already a shadow of their former selves. Rivers had carved deep valleys through the range. The tallest peaks had been worn down to gentler slopes. But the erosion did not stop. It never stops. Geologists call this period the Devonian, the age of fishes. While life exploded in the oceans below, the mountains above continued their slow collapse. Sediment from the eroding Caledonian Range spread across what is now lowland Scotland, forming thick layers of sandstone and conglomerate rock. These old red sandstone formations are visible today in cliffs and quarries across Scotland, and they are the fossil graveyard of the ancient mountains. The stone that once stood as peaks now lies flat as sedimentary layers, pressed into new rock by the weight of time. Then, 2.5 million years ago, the ice arrived. The Quaternary glaciation, the series of ice ages that sculpted modern Scotland, accelerated the erosion 100-fold. Ice sheets more than 1 kilometer thick spread across the land, grinding down the bedrock like sandpaper on wood. Glaciers flowed through the valleys, carving them into the U-shaped troughs we see today. Glencoe, Ben Nevis, Loch Lomond. Every major valley in Scotland was widened, deepened, and reshaped by ice. The glaciers did not just erode, they plucked. As ice moved over bedrock, it froze onto loose blocks of stone and ripped them free, carrying them hundreds of kilometers before dropping them as erratics. Boulders the size of houses, stranded in places they do not belong, proof of the ice's power. You can see these erratics across Scotland today. A granite boulder sitting on limestone, a chunk of volcanic rock resting on sedimentary layers. Geologists trace them back to their source, mapping the flow of ancient glaciers like forensic detectives following clues. Some erratics traveled over 200 kilometers from where they started, ripped from one mountain and abandoned on another. During the last glacial maximum, 22,000 years ago, almost all of Scotland was buried beneath ice. Only the highest peaks emerged above the frozen surface as nunataks, isolated summits in a sea of white. The ice was so thick that if you stood on top of it in central Scotland, you would have been higher than Ben Nevis is today. Think about that. The ice sheet was taller than the tallest mountain, and when the ice finally melted, 10,000 years ago, the mountains that remained were ghosts of what had been. The glaciers had carved them into new shapes. Peaks that once rose in smooth, weathered curves now displayed sharp arêtes, knife-edge ridges where two glaciers had carved from opposite sides. Corries, bowl-shaped hollows, marked the birthplaces of ancient glaciers, where snow accumulated and ice began its slow descent. The U-shaped valleys were the most dramatic change. Before the ice, Scotland's river valleys were V-shaped, carved by water over millions of years. The glaciers widened them, deepened them, and flattened their floors. Glencoe, one of Scotland's most famous valleys, was carved by a glacier over 300 meters thick. The result is a valley so deep and wide it feels like standing at the bottom of a canyon, with steep walls rising on either side. The ice did not just reshape the land, it erased mountains entirely. Softer peaks that might have survived wind and rain could not survive the grinding weight of a kilometer of ice. They were ground down to rubble, their stone carried away in glacial meltwater, deposited as moraines hundreds of kilometers from where they started. Ben Nevis is the best example. Today, it stands at 1,345 meters. But geologists know that the summit was once at least 600 meters higher, nearly 2,000 feet, before volcanic collapse buried the original peak beneath rubble and lava. That collapse created a caldera, a massive crater that eroded over time. And then, 60 million years ago, when Scotland separated from Greenland and the North Atlantic Ocean began to open, the mountain lost another 2 to 2.5 kilometers of rock, 6,500 to 8,200 feet. Gone, eroded, washed into the sea. If you add it up, Ben Nevis may once have stood at over 4,000 meters, 13,000 feet, taller than any peak in the Alps. Now it's one-third that height. The erosion did not happen evenly. Some rocks resisted better than others. Granite, the hard crystalline rock that forms Ben Nevis's core, erodes slowly. That is why Ben Nevis is still the highest peak. The softer metamorphic rocks around it wore away faster, leaving the granite standing like a fortress in a battlefield of rubble. But even granite loses. The average erosion rate in Scotland today is roughly 0.03 millimeters per year. That is 30 meters per million years. It does not sound like much, but over 400 million years, it adds up to 12,000 meters of lost elevation. That is 39,000 feet, more than the height of Everest. That number is theoretical. Erosion rates change over time depending on climate, vegetation, and tectonic activity. But the point remains, given enough time, erosion can erase anything. Mountains that once scraped the sky are now rolling hills, and eventually, even those will be worn flat. The Scottish Highlands are not unique. The Appalachian Mountains, the other half of the Caledonian Range, tell the same story. Once as tall as the Rockies, maybe taller, they have been worn down over hundreds of millions of years into gentle forested ridges. The highest peak, Mount Mitchell in North Carolina, stands at 2,037 meters, 6,684 feet. That is less than half the height of Denali and less than a quarter the height of Everest. But 400 million years ago, Mount Mitchell and Ben Nevis were part of the same towering range, connected across what is now the Atlantic Ocean. The connection is not just theoretical, it is visible in the rocks. Geologists studying both sides of the Atlantic found identical formations, the same types of metamorphic stone, the same patterns of folding and faulting, the same story written in layers of ancient crust. If you take a rock sample from the Scottish Highlands and compare it to a sample from the Appalachians, they match. Same mineral composition, same metamorphic grade, same age. They were formed in the same event, the Caledonian orogeny on one side of the ocean, and the Akkadian and Alleghenian orogenies on the other. Different names for the same process, continents colliding, mountains rising, and then slowly eroding away. Scotland and Appalachia are not the only remnants of this ancient range. The Atlas Mountains of Morocco, the Anti-Atlas of Algeria, parts of Scandinavia, and the mountains of Greenland and Newfoundland are all fragments of a colossal mountain system that stretched across Pangaea 400 million years ago. Imagine standing on one of those peaks. You could look east and see mountains extending unbroken across thousands of kilometers, from what would become North America, through Greenland, across Scotland and Scandinavia, all the way to what is now North Africa. One continuous range, taller than the Himalayas, stretching across a supercontinent that no longer exists. And now, scattered remnants, worn down, separated by an ocean that did not exist when the mountains were built. When Pangaea was whole, you could have walked from Scotland to North America without crossing an ocean, and the mountains you walked through would have been among the tallest on Earth. The Caledonian Range is not alone in this fate. Across the planet, ancient mountain ranges that once rivaled or exceeded modern peaks have been worn down to gentle highlands. The Ural Mountains, which divide Europe from Asia, are the eroded stumps of a range that formed 300 million years ago when Siberia collided with Eastern Europe. Geologists estimate they once stood as tall as the Alps, perhaps taller. Today, the highest peak barely exceeds 1,800 meters, Most of the range consists of rolling hills covered in taiga forest. The mountains that once defined a continental collision are now so low that roads cross them without tunnels. Eroded into simple hills, their scale has been lost to time. The Brazilian highlands tell a similar story. 2 billion years ago, long before even the Louisian gneiss formed, Brazil was part of a mountain-building event that created peaks potentially rivaling Everest. What remains today are rounded hills and plateaus, worn so flat that the landscape is dominated by tropical savanna rather than alpine terrain. The mountains are gone, and only the ancient metamorphic roots remain, exposed by 2 billion years of erosion. 2 billion years of wear leave only roots. Even the Great Dividing Range in Australia, the continent's most significant topographic feature, is a ghost of greater peaks. Formed during the same tectonic episodes that built the Caledonians, it once stood much taller. Now it is a series of plateaus and gentle ridges, with the highest point, Mount Kosciuszko, reaching just 2,228 meters, barely half the height of the modern Alps. These ranges share a common pattern. They are old, and given enough time, erosion always wins. Now, if you want to see what the Caledonian Mountains might have looked like at their peak, you have to look elsewhere. Himalayas, the Andes, the Alps, ranges that are still young, still rising, not yet worn down by the relentless patience of erosion. But even they will fall. The Himalayas are rising at roughly 5 millimeters per year, pushed upward by the ongoing collision between the Indian and Eurasian plates. Everest grows taller every year. But erosion is working just as hard in the opposite direction. Glaciers carve the slopes. Monsoon rains strip away billions of tons of rock. Rivers carry the debris south into the Ganges and Brahmaputra, depositing it in vast deltas. One day, millions of years from now, the collision will stop. The mountains will stop rising, and erosion will do to the Himalayas what it did to the Caledonian Range. They will vanish. Mountains are temporary. That's the lesson written into Scotland's geology. They rise in violence, in the grinding collision of continents, in the slow upward push of tectonic forces. And they fall in silence, in the quiet work of wind and water, in the patient sculpting of time. The rocks remember. The Louisian gneiss, 3 billion years old, survived the rise and fall of mountains we'll never see. It will outlast everything. Long after Ben Nevis has been worn to sea level, long after Scotland itself is unrecognizable, those ancient stones will remain, holding the memory of deep time in their banded layers. But for now, the highlands stand as monuments to what once was. When you climb Ben Nevis, you're not just reaching the highest point in Britain. You're standing on the remnant of something far greater, a peak that once towered over Europe, part of a range that stretched across an ancient world, taller than anything in the modern landscape. 400 million years of erosion can't erase that story. It's written into every rock, every valley, every ridge. The mountains that made Everest look small are gone, but their ghosts remain. And if you know where to look, you can still see them, in the stone beneath your feet, in the shape of the land, in the slow, patient work of geology that built them up and tore them down. Scotland's mountains were taller than Everest. Now they're hills. One day, they'll be flat. And the only evidence they ever existed will be in the rocks, waiting for someone to read them. That's the power of deep time. That's the story of the Caledonian Mountains. That's what 400 million years can do. And it's not done yet.